carry on our discussion on unitary matrix. So the next thing that we are going to do is a very interesting topic we call the QR factorization. So that's a beautiful algorithm that allows you to take any matrix, okay, of any order, should be non-singular, and then factorize it into a unitary matrix and an upper triangular matrix actually. So if A is a, say, m by n matrix, okay, it's say m n by n matrix with, say, entries from F, where F could be, as mentioned earlier, set of real numbers or set of complex numbers, then this factorization algorithm tells you that you can always find a unitary matrix, okay? You can find a unitary matrix and an upper triangular matrix, okay? That's a upper triangular matrix, okay? The upper triangular matrix has a form of the case that, okay, you have this matrix in which the non-zero entries appear on the upper part of the triangle actually, you know, including the diagonal, and all entries above the diagonal may be zero or non-zero, but all entries below the diagonal element are all zero actually. So what QR factorization proposes, so take a matrix with, say, entries from real numbers or complex numbers. You can always find a unitary matrix and an upper triangular matrix such that their product is equal to the A. In other words, A can be factorized into a unitary matrix and an upper triangular matrix actually. Okay, that's a wonderful application. You know, uses of what you call unitary matrices. We will see some of the beautiful applications of this algorithm immediately in upcoming parts of the discussion, and later on during the course actually, that there are several benefits of having such factorization actually. For example, one of the benefits would be that if you have say a consistent system of equation, then you have a very stable algorithm. This factorization algorithm or this factorization is going to provide you a very stable algorithm to solve that consistent system of linear equation actually. It's going to be a bit expensive than Gaussian elimination or all other method, but you know, it's a stable method. You can take a complicated matrix and compute its, say, determinant through what you call QR factorization. Even you can take, for example, an inconsistent system. This factorization allows you, we'll see it basically, this system allows you to calculate not the exact solution obviously because the system is inconsistent, but a nearest solution, a best approximate solution for that system actually. Okay, so it has lots and lots of applications. So this algorithm is a very interesting algorithm actually. So how algorithm works? Okay, so how algorithm works. Let me give you the recipe for the algorithm actually. That consider if A is a matrix in which there are n columns, okay, so m by n rows and n columns, say A1, A2 and AN represents, say, n columns of the matrix A actually. So these are not numbers, but these are column vectors actually. So there are n column vectors in matrix A in which there are n entries. Okay. And then the Q is, so this would be something that is given to us, or it is known to us actually, and our task is to find so if this matrix is m by n, then this matrix must be m by n, and this matrix will be n by n actually. So our task is to find an m by n unitary matrix and n by n what do you call rectangular matrix, n by n upper triangular matrix, and then their product should give us what do you call an m by n matrix actually. By unitary matrix Q, okay, because you might have seen that okay, the unitary matrices are always squares. We may interpret it actually in the case that Q is a kind of a matrix in which all columns are independent of each other, and they actually form an orthonormal set actually. Okay, all columns are orthonormal, mutually orthonormal actually, orthonormal vectors. Okay. Anyway, so the Q is going to be a matrix that we are interested in finding, Q1, Q2, and Qn, while these Q1, Q2, Qn represents the n columns of what you call Q matrix, in which every column has m entries. So it's n by m matrix. So this Q1, Q2, Qn, again they are not simple entries, they are not numbers, but they are column vectors actually. And R, I'm going to write it explicitly, is going to be a matrix that goes like R11, R12, R1n, and R22, R23, and so on and so forth, R22n, okay, and so on and so forth. So all entries 0 except the last R and n actually. So this is really is the upper triangular matrix that we are interested in. So so this algorithm is an algorithm that tells you that if you give me a matrix A, then I will give you a matrix Q in which all columns form an orthonormal set. Okay, so they are orthonormal vectors, and an upper triangular matrix R actually. So using A we can find these. So what is the algorithm? The algorithm is really simple. I'm going to talk about this algorithm first and do one example in the case when the entries are from the set of real numbers actually. Okay, the entries are from the set of real numbers. For a set of complex number, I'll just mention the algorithm. Okay. By the way, in our next part of discussion, I will also justify this algorithm actually, that why this algorithm the way it is actually. So what is the proof or derivation or justification for the algorithm, that why this algorithm, works actually. Okay. And this is important. It's not enough to just learn a step-by-step method. Being mathematics student, you have to kind of also learn that why something is true, why some method is working actually. Okay, so what is the recipe for constructing these Qs? The recipe is very simple actually. Take these n column vectors, okay, so apply Gram-Schmidt process to construct n orthonormal vectors actually. So take these n vectors, okay, n column vectors, and using the Gram-Schmidt process, turn them into an orthonormal set of vectors actually. And we know already that how to do it actually. Okay. So if I want to, for example, compute my Q1, okay, so the algorithm goes like this. This is going to be what you call the vector A1 divided by the magnitude of A1. Okay, this is what is really your vector Q1. What would be Q2? Okay, Q2 is going to be A2 minus A2 dot Q1 times Q1. Just follow the standard, what do you call, Gram-Schmidt algorithm. Okay, the Q3 is going to be the vector A3 minus A3 dot Q2 times Q1 minus A3 dot Q1 times Q1. Okay, simple Gram-Schmidt process. We know this is basically the orthogonal projection. We will talk about these projections in a moment in our next discussion as well. So in general, if you want to, for example, find Qn, the Qn is going to be An minus the sum that goes from I equal to 1 to n minus 1, okay, of An dot Qi times what do you call Qi. So finding this unitary matrix, or the matrix which has really what do you call independent columns, it's not difficult. Just take the vectors from A, the column vectors from A, apply the Gram-Schmidt process that we have learned, and construct the n vectors actually. Okay. Now, what would be the R matrix? The R matrix is also a matrix that is easy to what do you call compute actually. This is very easy to compute. Okay, and it should be computed in this manner. So the first entry, okay, if I say for example write the algorithm that okay the Rij okay is going to be an entry. So first task will be to find the cube. This will be the step 1 of the algorithm. First find all cubes. Once you find all cubes and you have A's, then using these cubes and A's you can compute what do you call this upper triangular matrix actually. So the Rij is going to be Qi dot Aj. Okay, Qi dot Aj. Okay, by the dot I mean the dot product in Rn actually. Okay, so the R matrix is then going to be I can write this as that this is A1 dot Q1. This will be the first entry. Okay, A1, or I can also write this as Aj dot Qi. Okay, so if I have R11, so it's going to be A1 dot Q1. R12 is going to be A2 dot Q1. It's going to be A2 dot Q1 up to An dot Q1. Okay, this is the first row. What would be the second row of this rectangular matrix? So it's going to be R22, so it's going to be A2 dot Q2, okay, up to A2 An dot Q2. Okay. So in the first row Q1 is fixed, A1 is changing, you know, A's are changing. In second row Q2 is fixed and A's are changing, and so on and so forth. The last entry is really going to be An dot what you call Qn. So very simple algorithm. Okay. How can I take a matrix and factorize it into Q and R? First, take your A, apply Gram-Schmidt on A's, and construct these n orthonormal set of vectors. By the way, I missed something. To orthonormalize it, you always have to divide by the magnitude of the same vector that you have above actually. Okay? The same vector that you have here divided by the same. So similarly, this divided by the magnitude of the same vector denominator, and obviously this divided by the magnitude of the same vector as above actually. Okay, so this would be the correct orthonormalization of the vectors A1, A2, An. And R can be computed as this actually. You can ask the question actually, why the Q's have these formula and R has these formula, I will justify all these formulas in the next part of the lecture actually. Okay, so in this part I've just proposed the algorithm, and I'll use one example to illustrate that how this example works actually. Okay, so let's do one example of applying the QR factorization and solving the, what do you call, the problem. So here's one example. Take a matrix A. Okay, you can have any matrix. So 1, 1, 0. Say you have 1, 0, 1, and 0, 1, 1. Okay. Now A1 is going to be the first column. In other words, it's a vector 1, 1, 0 transpose. Okay. When I'm going to transpose it, it's going to be a column. A2 is 1, 0, 1 transpose, and A3 is 0, 1, 1 transpose. Okay, this is what it is actually. So these are the three vectors. While doing our calculation, I'll not write this transpose again and again. Okay, I'll treat them as vectors. Okay, but you have to keep in view that these vectors are basically columns of matrices. So whenever you have to, for example, compute your Q's are going to be vector, but you have to put them in column wise manner actually. Okay, this is what is important. I'm not going to write this transpose again and again while doing our calculation actually. Okay, so let's do the calculation. Let's start with, say, for example, the vector Q1. Okay, so the Q1 is the vector A1 divided by the magnitude of A1. Now the vector A1 is obviously 1, 1, 0 divided by the magnitude is 1 square plus 1 square plus 0 square. Okay, so this is going to be square root of 2. So you can say that the first vector is the Q1 is 1 over square root of 2, 1 over square root of 2, and 0. Okay, so you can compute the A1 in this manner. Then what would be A2? The formula is there. You just need to take what you call these vectors. Okay, A2. So you know it from the matrix. You know the Q1. You have just calculated it. Substitute them here and calculate what do you call the vector. So let's first calculate, for example, the numerator of this Q2. So when you will calculate A2 minus A2 dot Q1, I'm not doing these calculations, I'm just going to write the answer actually. Okay, so you know the A2, so A2 is 1, 0, 1. So take its dot product with Q1, and whatever scalar you will get multiplied with Q1 and then subtract actually. So after doing these calculations, you're going to get a vector that looks like, okay, 1/2, -1/2, and 1 actually. Okay, this is what that you're going to get. So what is my Q2? So the Q2 is this vector 1/2, -1/2, 1 divided by the magnitude of it actually. So 1/2 is square plus -1/2 is square plus 1 is square actually. Okay, so the Q2, if you simplify, after simplification, this is going to be 1 over square root of 6, -1 over square root of 6, and 2 over square root of 6. So this is my, what do you call, vector Q2 is. Okay. Similarly, if you take this Q2, Q1, A1 and A2 and A3, if you make the substitution here, okay, calculate this dot product and then these two vectors and then subtract it from this vector divided by magnitude, you're going to get Q3. So the Q3, so when I'm going to compute, for example, this top vector, okay, something that you're going to get is going to be -1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. Okay, so this is what that you can get actually. And Q3 is going to be this vector after calculation divided by its magnitude actually. So the magnitude of it is going to be 1/3 plus 1/3 plus 1/3. So which is going to be 1. So the Q3 is the same vector as above actually. Negative 1 over the square root of 3, negative 1 over the square root of 3, 1 over the square root of 3. Okay, so this is my Q3. And once I have my matrix Q3, okay, then what I'm going to do, I'm going to put these vectors as a column in my Q matrix actually, okay, in my Q matrix. So the Q1 is really 1 over the square root of 2, 1 over the square root of 2, 0. So it's going to be 1 over the square root of 2, 1 over the square root of 2, 0. Put it at column. So the Q2 is 1 over the square root of 6 minus 1 over the square root of 6 and 2 over the square root of 6. And third column of it is going to be negative 1 over the square root of 3, 1 over the square root of 3 and 1 over the square root of 3. So this is really is your matrix Q actually. Okay. Now as evident from this matrix actually that now you have the vector A's and Q's all. Okay. So our matrix in this case is going to be A1 dot Q1, A2 dot Q1, A3 dot Q1, okay, 0, A2 dot Q2, A3 dot Q2, and 0, 0, and A4, A3 dot Q3. Okay, so this is the rectangular matrix actually, so you can calculate it easily. So you know your Q's, you know your A's, just take their dot product and you're going to get what do you call the numbers actually. So when you're going to do the computation, so I'm not doing the calculation, I'm just writing it actually. I hope you can calculate the dot products. 2 over the square root of 2, 1 over the square root of 2, and 1 over the square root of 2. Okay, this is what is going to be the first matrix. 0, 3 over the square root of 6, 1 over the square root of 6, 0, 0, 2 over the square root of 3. So this is what is going to be our matrix actually. Okay. And so once you have this R matrix and Q matrix, you can actually verify that when you take the product of Q and R, you're going to get the matrix here. Okay. So that's what really is the algorithm. By the way, let me add one more thing. There is really a shortcut to find what do you call Q. Okay? There is a shortcut to find Q if A is if M is equal to N. In other words, if A and Q are square matrices actually. So if they are square matrices, there is even a shortcut actually to find the what do you call Q matrix actually. Okay. When M is N, Q would be a what do you call a unitary matrix, and if its entries are real, then this unitary matrix would be basically an orthogonal matrix actually. So Q is really an orthogonal what do you call matrix actually. Okay, Q is orthogonal matrix. That is that Q transpose is equal to the inverse of the Q. Okay, inverse of the Q actually. Now, if the algorithm then again it can be revisited in this manner. You know, yes, you have to do the Gram-Schmidt process and compute Q. But there is a shortcut to find R actually, okay? The upper triangular method, if the M is N, okay? Find Q. Now since Q is orthogonal and A is equal to what you call QR, where the R is unknown, we know the A and Q, then R can easily be found by simply multiplying the Q transpose on both sides. So if you multiply the Q transpose A, so it's going to be Q transpose QR, which is equal to R actually. So this means in order to find what do you call the matrix R, you don't have to find the dot products. Just do what? Transpose your Q and multiply it with A actually. Okay? Transpose your Q and multiply it with A and so what is shortcut to find R? First find your Q through the Gram-Schmidt process, and once you find Q, transpose it and multiply it with A, you're going to get your rectangular matrix R. But this would work when M is N. If M is not N, then apply simply this algorithm the way it is actually.